you know that's going to have a huge impact then, now, on how everything looks and how the structure is going to come across. And then what we have to do is figure out, well, what are the equations of motion for this system? Okay. All right. So what we can do is we can, as before, start constructing the quantities that matter here. In particular, what we're interested in is how does U, V, and W change as a function of time. And if you remember last time, this picture looks a lot like what we did before with that 2D shallow water wave problem. And so what I can do is do the same kind of thing as I did before. How about if we do the following? We all believe conservation of mass, conservation of momentum. At least if this thing's not moving near the speed of light, it's going to be fine. Okay? So, given that we have conservation of mass and momentum, we can construct those equations. And in particular, I shouldn't erase that, but fine. In particular, we're going to look at this slice of the plane, right? Now what matters to us is the xz plane here. And in that xz plane, I'm going to calculate conservation of mass, conservation of momentum along that direction. Okay? Here's what I'm going to end up with. These are the full equations without approximating anything. That's conservation of mass. That's what you're going to get. And it comes out the same way we derived conservation of mass previously. Then you have conservation of mass in both the x direction and z direction. So that's conservation of momentum, sorry, conservation of mass, conservation of momentum in the x direction, and here is conservation of momentum in the z direction. And I'll tell you what R is in a moment. Okay? There you go. 3 big PDEs, no assumptions made. And by the way, R here is basically tells you what's going on some surface on this direction. Okay? R is telling you, if I were to take a measure here, it tells me at some fixed, so if I were to take a plane across here, and or actually even cap it at some point and look at what happens to this surface of how the fluid is driving a plane across here, that's what R is to this distance. Was that? No, it's not density. Okay? It's this surface, how it's moving dynamically. And what I'm going to assume is the following. If you remember, last time we looked, we went up to the surface height h. And we said, well, suppose h is not moving a whole lot, or it's moving a small amount in relation to the other parameters in the problem. I'll make h constant at leading order. We're going to do the same thing here. No approximations to this point. And now what we're going to say is, no, let's assume that R is moving, but not much, at least to leading order. We'll say that at leading order, R is constant. Now, if R is constant, great things happen for you and for me, because then I can get a lot of things to go away. In fact, the first equation, basically, right, you end up with this. U of x plus, okay? This tells you that if you take the x derivatives of the u plus z derivative of the w component of velocity, this has to be equal to 0. And this is basically our incompressible flow condition. Okay? That's what we got last time.
That one was not incompressible.
Excuse me?
That one was not incompressible. But this one is. Like the one with the R. Yeah.
Sorry?
This one is compressible.
This is compressible. Right. So if this changes in time, in other words, you can take this fluid and squeeze it together so that now there's a time dynamic associated with it, so that you can get actually compression in a gas, for instance.
And then you get incompressible.
That's right. That's right.
It's not density in.
No. It could be related. This R is not the density of the fluid. R is this height of the fluid, but if you can't squeeze, it's like not being able to squeeze the density, right? Because remember, R tells you it's a volume cube like this, where from here out to the edge of that thing is R. So if that's not changing in time, it's like effectively saying that I'm not squeezing. So it's, if you want to think about it as keeping the density constant, we're assuming that the density is constant in this thing. That's equivalent to this thing. Okay? Okay, so incompressible flow condition under this assumption. And you can do reductions similarly to the other equations. And let me just show you what you get. Everything's going to follow exactly what we did previously in the 2D shallow water wave. In fact, here's what you're going to get. Recognize it? That was your homework 4. Sweet little pictures you got out of that thing. Okay? About vortex flow. But now, there is a big difference here. I mean, this is now in this xz plane, so who cares? I mean, right? Let's just talk about this for a moment. This now, this Poisson bracket, is psi of x, omega z, minus psi z, omega x. Okay? So now the variables are x and z. So it's this plane, the xz plane, versus our xy plane, which we had previously. Not such a big deal, really. And the omega we're looking at here not to be confused with w, which look the same. Sorry. That is, I'll try to make them look different. That's my velocity in the z direction. This is my vorticity, omega. That's omega, the vorticity. Okay? These are all w's. Yeah, and over here, finally, this is really omega, which is this vorticity. All right. It's nice and clear in the notes because there you use LaTeX and they have nice things. I don't have a LaTeX pen. It's probably just, if I had one LaTeX pen, it'd be easy for me. So it's not really my fault. I just got provided with simple black pens. I've requested these LaTeX pens forever. Okay, there you go. Stream function. But here's the big difference. The big difference for you is that now, what are your boundary conditions? All right, so you have a very nice set of equations here. But now, when we start thinking about boundary conditions, let's start thinking about what we want to do with this.